All right. So thank you everyone for joining this our research seminar series from Center for Transportation Logistics at IIM Ahmedabad. We are very excited to have with us today Professor Alexander from MIT. In fact, he's addressing a very critical problem in logistics, which is all about wildfire suppression. And we talk about courses, how important it is to suppress wildfires in a rapid responsive manner. And optimization is indeed the right tools here to leverage for this particular important research question. So we'll talk about predictive and prescriptive analytics towards optimizing the wildfires in the forest. And a bit about our speaker today, Alexander. I know him from several years. We are together part of the transportation science and logistics community, but he's a Maurice F. Strong Career Development Professor and an Associate Professor OR and Statistics at the MIT Sloan School of Management. His research develops algorithms for large-scale discrete optimization, and of course, optimization on uncertainty for different applications. It could be urban mobility, sustainability. I know he does a lot of work in aviation as well, and of course, socially good operations. In his career, he received several awards, including the very prestigious Inform Danzig Dissertation Award, the Best Paper Prize for Informs TSL Community, the Harvey Greenberg Research Award for Informs Computing, Pierce Keller Best Paper Award for Informs Health Applications, and Best Paper Award for Informs Data Mining and Decision Analytics. So we're very excited to have him with us today. And yeah, with that, I will leave the floor, rather the Zoom, to Alex over here. Thank you so much, Alex, for joining us this evening.
Thank you so much for having me. Thanks everyone for joining. It's a pleasure for me to visit you virtually. As I mentioned in the introduction, I'm more than happy to entertain any questions that you have on the way. I'm going to be going through my presentation to this paper, but yeah, the goal is really to make this as interactive as you'd like. So feel free to stop me. So I'm going to go ahead and share my screen. So as Devjit said, my name is Alex Jaquillad. I'm a faculty at MIT. And so this is a paper that is called Predictive and Prescriptive Analytics toward Optimizing Wildfire Suppression. This is joint work with Leonard Boussioux, who is now an assistant professor at the University of Washington, and Jacob Wagstress, who is a former master's student at the Operations Research Center at MIT. So just to give a little bit of background, as Devjit said, this is my overall research agenda in large-scale optimization with different applications in transportation and logistics. So I started my career in air traffic management, and then I moved to demand responsive transit, urban mobility more generally, a little bit of ride-sharing operations as well. And more recently, I started a research agenda in logistics, transportation logistics more broadly defined, with some applications in the decarbonization of hard to decarbonize logistics sectors like long-haul trucking or cloud supply chains, for example. These are very intensive logistics activities that are responsible for a significant fraction of our greenhouse gas emissions. And so any optimization can help us in this regard. And finally, even more recently, I started a new research agenda on the optimization for social good operations. The idea being that a lot of problems have underlying logistics challenges. And if we solve these logistics challenges, we can make the underlying systems much more efficient, much more effective. For example, I have worked on vaccine allocations. I have worked on organ allocations. And I have worked more recently on the wildfire suppression, which will be the focus today. So the reason why I'm mentioning all this is that it's actually quite interesting to think about these different areas, and for the students, the graduate students in attendance, what I have found very useful myself is to start with one particular problem. In my case, it was air traffic management. Go very deep and understand very well both the context, the domain, and the technical problems. Develop methodologies for this problem, and then at some point, take a step back and say, okay, so what are we really doing? What is this problem, and what is the broader class of problems that we can address? And then by doing this mental model, and if we correlate to this, the emerging challenges that are faced in the world, like in this case, urban mobility, decarbonization, social good operations, then we can really go from problem to adjacent problem, and actually go into expand the span of our research in a way that is quite impactful from a practical standpoint, but also quite fruitful from a technical standpoint, because by looking at new problems, we look at new structures, and by looking at new structures, we develop new methodologies, and this is really that back and forth that has been driving this scientific investigation for me. So a couple of if we think about transportation and logistics very broadly, basically what we are optimizing is, I think, spatial temporal resource allocation, right? Which is what is at the core of vehicle routing, of network design, of facility location. All of these problems that are core to transportation and logistics involve allocating scarce resources over time and space. And actually, this problem of spatial temporal resource allocation has been arising elsewhere, and this is what actually drove me to different type of applications in social good. And so I want to mention these three applications. Number one is vaccine allocation. So this is a paper that we wrote a couple of years ago that started obviously during the COVID-19 pandemic. That was a very, very difficult problem. So we had a big sprint to deliver short-term impact in 2021 because of the urgency of the pandemic. And then we developed a more general methodology and published a paper in Operations Research a couple of years ago. And so this problem involved allocating a scarce pool of vaccines across different regions, each of which is governed by basically the pandemic dynamics, right? More people get sick, more people recover, and so on and so forth. And so the question is how to use vaccine distribution as a lever to combat and to fight the pandemic, to alleviate the impact of the pandemic. And again, by doing spatial temporal allocation, that is determining who gets the vaccine when, who to prioritize, and how to play with the flexibility that we have in vaccine distribution, we can actually increase the impact of a vaccination campaign. In this case, we found that optimization could contribute to an extra 20% of saved lives over the course of a vaccination campaign. More recently, we started looking at organ transplantation. So organ transplantation is an important part of healthcare systems, obviously, but at the same time, there is only, I think, 80% of, so I'm going to, yeah, okay. There is only 80% of the organs that are donated that are actually utilized. And so the question is how to increase that. And we've been partnering with a local startup that is developing a device to transport organs and maintain organs in good conditions. And the problem now is like how to basically allocate these machines and the underlying vehicles and the personnel in order to make these logistics operations as efficient as possible. And so, this is these are the type of problems that are emerging elsewhere. And I'm going to show today another one which will deal with wildfire suppression, where again we're going to have an important problem of spatial temporal allocation. And so that's going to be the focus for today. So trying to say is that vehicle routing, network design, facility location do not only arise in the context of last mile deliveries and ride sharing operations that we're very used to in transportation, but also in other contexts, which we are going to be talking about today. Okay. And again, as I mentioned before, by looking at new problems, we are looking at new methodologies, and that has driven my own methodological innovations. And so in today's talk, the challenges lie in number one, very difficult optimization structures, and number two, different data-driven problems that lead to innovations in large-scale optimization methods and in machine learning. In parallel, in other papers, I have contributed more to online optimization and field experimentation for different contexts. All right, so let us dive into wildfires. So the impact of wildfires is unfortunately not news to anyone. We are seeing them in the news very often. Perhaps the most significant example to date, at least in the United States, was the very large wildfire season in Los Angeles in January 2025. That has led to a very significant death toll, to a huge land mass that has been burned and destroyed, and a lot of residents that had to flee and to leave their homes. So obviously an incredibly large social, human, and economic impact. And actually, these intense fire seasons are broader. We see them in the news very often in Canada, in Australia, in Greece, and many other parts of the world. And actually, if we think about it from a logistical standpoint, then the problem is basically how to attack these wildfires with limited resources. And this is a problem that has been relevant for a long time, way before the Los Angeles fires. The chief of the U.S. Forest Service, Randy Moore, wrote a report that had the following quote that was saying that basically we are in triage mode, where the primary focus must be on fires that threaten communities and infrastructure. That means that essentially the number of resources that we have is not sufficient to just attack each fire individually as we would like to do, but we have to allocate scarce resources across wildfires in order to maximize the impact of a suppression activity. Okay, and so now we're thinking about how to allocate these resources in the most effective manner to fight these wildfires. And so now the problem is not only a kind of fire engineering problem, which is how to suppress a fire, but also a logistical challenge, which is how to allocate scarce resources across wildfires in a spatial region over time. Okay, and so that's the idea. So I'm going to go over that paper in detail. We're gonna, basically the main contribution will be to develop an optimization problem. So a model and a branch and price and cut algorithm for prescriptive wildfire analytics. So we're going to show some computational results that will show that it can scale to very large problems that are relevant in practice. And in addition, for the machine learning enthusiasts in the room, we are going to actually use data to learn how the wildfire propagation dynamics. And what is very interesting is that there is a significant endogeneity problem in that machine learning context. And so we're going to use a double machine learning method to estimate kind of the treatment effects in econometrics terms, and I will go over that in detail. And we're going to then use this data-driven wildfire model with the optimization model to kind of allocate our resources over time and space. Okay, so before jumping into the optimization model, let me provide you with an overview of the data that we have available. So you have satellite data from Google Earth Engine or other sources. So we use some post-process data from the US Forest Service that give us basically the daily wildfire mask. So it gives you basically which area is currently burned by each fire on each day. Okay, so you know that on day T, you know that on day T+1, you're trying to basically, from a machine learning standpoint, anticipate what's going to happen on day T+1, and from an optimization standpoint, alleviate what's going to happen on day T+1. At the same time, with, again, the same satellite data, you have access to a lot of covariate information that captures meteorological conditions. So elevation, winds, temperature, humidity, precipitation, drought, vegetation, population, energy release components. All of these are meteorological data that do impact, and quite significantly, the evolution of the fire. And then we have access to new data that basically give us the historical resource assignments to wildfires at the daily level. So basically what we know is that on August 10, there were 10 firefighters that were allocated to this wildfire, 40 firefighters that were assigned to that wildfire, and so on. So just to provide a little bit of a visualization. This is the distribution of the burn area on each day, on the total burn area at the end of a fire, and on the number of personnel that was assigned on the highest suppression day across all the wildfires. And what we see is that all of these distributions basically have this sort of exponential shape, geometric shape, which basically give us a sense of the huge variability. You have a lot of small fires, right, with a little bit of personnel and a small burn area, but then you have a few very high impact fires. And so the question is how to manage that entire portfolio, so to speak.
Alex, a quick question for you.
Yes, please.
I was wondering, so is the objective to minimize the burn area, and also is it more about responsiveness? How quickly can you minimize, or it is just what is the clearly objective here?
Yeah, so I'll be going over that, but in our implementation, we are going to be minimizing total burn area.
Got it.
In follow-on work, we're looking at how to suppress one fire at a much more microscopic level. So the scope of this study is tactical. So we are allocating resources across a geographic region that is relatively large, and with a lot of fires, right? And so the idea is like how to manage each fire. I mean, how to manage the portfolio of fires in a sense. So each fire is a dot, and we're trying to minimize the size of the dot. In follow-on work, we're diving into like one fire, and we're trying to go much more at a much more microscopic level to one fire. And then here in that case, it's not only about burn area. We want to minimize damage to local properties. We want to minimize damage to local infrastructure. For example, power lines need to be saved if possible, these type of things. We do not have the granularity in the data here to make these assessments, so we are using burn area as a proxy. So that's one of the limitations.
Burnt area is closely related to time as well, so that is closely related. But what are some of the interventions here? You mean resource allocation would be in terms of fire extinguishers? What are resource allocations here?
Yeah, so I'll be going over that, but again, what we are allocating here are crews. In the US they're called hotshot crews. They are basically the crews of the highest levels of training and expertise, and they usually come with the teams of 20, again, hotshot firefighters. And then at the same time, they come with other resources, right? So all of the material and everything. So the crew is the unit of assignment here.
Got it.
There's a question on the chat. Did you fit and test which distribution fit better? You mean to these daily burn area and total burn area? No, we did not, because we do not really do that. We do not really need that in the optimization. This is more like a motivation and visualization slide. What we will do later is to fit a machine learning model to predict burn area on day t+1 as a function of information on day t. So that's going to be the data-driven challenge.
Sure.
Okay.
Thank you.
All right. So this is basically what the real world looks like. You look at where your fires are. So that's the number of fires in each state in the United States and by color. And then the little dots, the black dots are the individual fires. And then what you have in blue are the stations for our hotshot crews, right? So That's what I mentioned in a response to your question. That's where the crews are actually located. And obviously there is correlation, but it's not perfect. And then the US is a big country, and so anyway, so anytime a fire gets active, then we need to decide whether we send a hotshot crew right now, whether we keep monitoring it, and we will perhaps send a hotshot crew in the future, and how to basically manage the availability of these crews. And the final thing that I need to say here is that these assignments are heavily regulated. It is a very hazardous activity to suppress fires. An article in the New York Times actually yesterday showed that it is heavily correlated with lower life expectancy and other health hazards. And so it's very important to respect rest periods and these type of things. And so so there are a lot of like hidden constraints, so to speak, in these assignments.
But Alex, just to think about it, it's a very complex problem, huh? Because the fire is also moving is dynamic, it's not static.
100%. That's why we need spatial temporal allocation. We need to think about like the fire season in a sense.
Yeah.
So, okay, so let me go now into the optimization problem. We're gonna jump into that now that we have this problem in mind. And basically, what I want to say is that we're going to do two things. We're going to do crew routing and fire triage. So let's think about crew routing for a second. If I think about this picture, and I see each dot as a fire, and each star as basically a depot, and now it looks like a routing problem, right? In a sense, you have a bunch of crews and you want to route them from fire to fire in order to extinguish them. You could have the same thing with a truck and packages, and it will be a routing problem. The main difference, exactly to your point, Debjet, is that the fires grow when you leave them alone. So if you do not deliver a package today to a customer, you can go tomorrow, it's going to be the same package. If you do not suppress a fire today, you will go back tomorrow, but the fire will look different.
Yeah.
So that is the idea of the paper, basically. Is that basically we're doing a crew routing problem with endogenous propagation dynamics, because the demand at day t+1 depends on your decisions at day t.
It's kind of similar to the organ transplantation or something, right? Because if you do it in time, rapidly, it's better. Delays, the consequences are quite bad, right? Beyond.
Yeah, it is.
The sooner, the better receptibility or whatever.
I think it's very different to the vaccine allocation problem that I worked on, because the state of the pandemic at day t+1 depends on your vaccination decisions on day t. So in a similar fashion. Except that in the vaccine allocation problem, there was no real routing problem. It was more of a resource allocation. Here, we also need to think about the routing.
Yeah. No, I was thinking about any product that deteriorates significantly over time. It could be intensive, maybe healthcare, any organ transplant, or any of those.
Oh, yeah, absolutely. And so, okay, so now, exactly, in the healthcare system, people think about triage prioritization all the time, exactly to your point. So if now we forget about fires and we go to the hospital, then you're in an emergency department. There are thousands of papers in our field that look at patient prioritization and patient triaging in emergency rooms. You have a bunch of patients. Some of them have a broken finger. Some of them are bleeding to death. You have to make prioritization decisions, same way. But now we have and then it's the same thing in fires. You have small fires, big fires. Good, same thing. However, your fires are dispersed in space. So attending to a high-risk fire requires travel, and travel means basically idle time. And that is something that we don't have in hospitals. So in a sense, what the paper is doing is that it is combining a routing component, which is all of the travel optimization, and a triage component, which is managing the dynamic evolution of the fires. So just to say the same thing in English, we have a vehicle routing problem with endogenous demand because the fires grow while unattended, or at least the fire growth depends on your suppression decisions. And you have a fire triage problem with heterogeneous switching costs and a bunch of routing constraints related to fatigue and policies and regulations that are required altogether to combine a routing and a triage model. I'm going to jump into math now, but if there is any question, I'm happy to take them. Otherwise, the plan is to formulate the problem mathematically and to develop some branch and price and cut algorithm over the next 20 minutes.
I think Alex explained the problem very well. It is what is so far the most exciting for me is the endogenous demand, right? If we don't attend it right now, it's going to become a bigger problem very soon. So how do you prioritize?
Yeah.
That's very unique.
Yeah. Okay. Great. So this is the idea. So let's look at you can see my cursor, I suppose. So this is the problem on the left-hand side. The problem on the left-hand side is basically the crew routing problem. So this is a time-space network. Every node represents a location, a fire, and a timestamp. So this is a time-space network, which is very common in transportation and logistics for those of you who are used to these types of models, right? Airline scheduling, transit scheduling, even vehicle routing with time windows. We use these representations all the time. So in this case, your crew will go from fire 1 to fire 2. I mean, basically, we'll suppress fire 1 at time 0, at time 1, then we'll go to fire 2, then suppress it, then go to the base. And so the only difference with a usual time-space network is that we are adding another replicated time-space network on the right. So why is that? It means the one on the left means that you have not rested yet, and the one on the right means that you have actually rested. So this is a representation just to impose the rest requirements for every crew. Over the span of 2 weeks, 14 days, you have to rest for 2 nights in a row at your base. Otherwise, you are in violation of your policy requirements. Sorry, I saw that there is a question. Yeah, it's a combination of logistics and life science problem. You can very well view it that way, Francois. Okay, so this is our time-space network for crew operations, very classic in transportation. On the right-hand side, we now have what we call a fire time-state network. So we are representing, so this is the key idea for the dynamics of the fire. We are representing every fire as a dynamical system. Okay, so here is the limitation, as a deterministic dynamical system that is governed by a dynamic programming formulation. So we have a state. So the state, we'll talk about the state in a second, but we have a state variable at every time period. We make an action, and then at each time period t plus 1, st plus 1 will be a function f of the current state st and the decision xt. A very generic dynamical system representation. So in this case, my state variable represents basically the risk of the fire, like gone, very minor, moderate, severe, extreme, catastrophic. This is an illustration only, of course. Then at time 0, your fire is in the minor state. And then your transition depends on your allocation. So if you allocate 4 hotshot crews to that fire, then it will transition from minor to very minor and from very minor to suppressed. If you allocate 2 crews, then you will stay in the minor state, then go to very minor, allocate 1 crew, and then suppress it eventually. If you allocate nobody, then your fire will blow up from minor to moderate, from moderate to severe, and then from severe to extreme, and then you're like, oh, whoa, let me actually allocate some crews, 2, 6, 6, 6, 6, 6, whatever, and then you will start suppressing it. It's an illustration, but it's actually quite representative of what we observe in practice, where your allocation impacts the future evolution of your system. So, okay. Does that make sense? I'm going to monitor the questions for a second. Q&A. There's a question from Himanshu, which is whether preemption is allowed. Can a crew abandon a fire mid-shift? Yes. Is realized now and has more priority. Yes, preemption will be allowed. We are making dynamical decisions, and so at every time we are going to re-optimize the allocations. However, preemption comes with a cost, which is not the case in traditional queuing systems, because of the travel cost. Right, so that's the core trade-off. And travel cost is not only a cost that you pay, cost of fuel or whatever. It's cost of idleness. While you leave, you move, and you start working again, you basically lose time, and time is the essence here.
I have a precursor question, Alex, here. So is it that you're learning the fire spread behavior under different times? So how do you model the right dynamics here?
So that is what the machine learning model will do at the end.
Do that, right? Yeah. Okay. I was
guessing. So basically, you can view the machine learning model, the goal of the machine learning model, as creating the fire state network that I'm presenting here.
Makes sense. Thank you.
Okay, good. So that's where we are. And now, from an optimization standpoint, what we're going to do is that we're going to optimize the path of every crew on the time-space network and the path of every fire on the time-state network. However, they will be coupled because my crew allocations, my crew path on the left will determine the number of crews that are active and suppressing any fire at any time. That will basically give me the little numbers here on the right-hand side that will therefore determine the path of the fires. So I need to ensure the consistency between my decisions on the left and my decisions on the right. So that's what's going to be difficult from an optimization standpoint. So we're going to optimize that with path-based variables, where I'm going to have ZP as an indicator of whether the crew takes path P1 or not 0. And then I'm going to have YQ variables that will determine whether fire takes path Q, yes or no, 1 or 0. And again, they will be coupled. So this is the full representation on a time-space network. We are basically minimizing travel costs and fatigue for the crews and fire damage. The number one objective, going back to your answer to your question earlier, Dibjit, is fire damage. So DA is basically the total. We can think about it as total burn area. I think that's a good proxy for the objective. Then we have flow balance constraints for each crew on their time-space network. Flow balance constraint for each fire on their time-space network. And then we have the linking constraint that says that the supply of crews meets the fire demand at all times, but the fire demand depends on the Y variable, depends on the path that you're choosing.
And the time would be here every minute?
No, every day. And these are all daily allocations.
But the fire will be spreading quite rapidly, right? So would it be okay to do it like a short intervals? Or but crew?
Yeah, we're thinking of we're trying to do it every 3 hours right now. The problem is that the granularity of our crew allocation data is daily. And so we have to do a little bit of extrapolation in the data-driven part.
I'm struggling with one question. Maybe you can help me, Alex. The crew assignment is a longer-term decision, whereas the fire spread is more operational, right? It is dynamic thing. So how are we really understanding, how are we trying to match the long-term decision with very short-term dynamic movement of fire?
What we don't do in this paper is really the microscopic assignment of like, you as a crew, you should do this and this, attack the fire this way, that way, and then the fire will propagate this way, that way. We don't model the front line of the fire. We're just trying to capture that at a more mesoscopic level, not macroscopic level, but mesoscopic level, which is, well, the fire will basically grow by that much or this much. So again, it's the question is that what is the scope of the model? In this case, the scope is regional, and so the representation of each fire is relatively coarse, as opposed to, let's say, having the scope of like one fire with a more granular representation.
Thank you.
No, thanks for the question. That's really helpful. Okay. So now we are going into the actual formulation that we're going to use, which is a set partitioning formulation where we are optimizing over path for crews and for fires. So ZPYQ, as I mentioned before on the slide, ZP will govern the entire crew path here, YQ the entire fire path there. And so we are still minimizing fire damage. We have set partitioning constraints that will ensure that one suppression plan will be assigned to every fire, that one route will be assigned to every crew. And then we still have this same linking constraint that says that the crew supply will meet the suppression plan demand at all times. So at any time, for any fire, the number of crews that are required for that fire to follow that path is less than the number of crews that are allocated to that fire. Based on the crew routes. So in a sense, again, for all of the transportation and logistics aficionado in the audience, if you look at, let's say, the first two, like one blue box, one red box, and half of the green box, this is a set partitioning problem, right? You're minimizing crew routes, you have one route per vehicle, and then you have some demand constraint. The challenge here is that we have what we call a two-sided set partitioning formulation, because we have this on crews, we have this on fires with the linking constraints. So we're going to apply a column generation idea here, where we're going to generate these routes iteratively in order to make the formulation more tractable. So the idea is very standard. We have a master problem that will solve the relaxation of this problem with a subset of crew routes and of fire plans. Then we have a sub-problem for each fire, a sub-problem for each crew that will look for a path of minimal reduced cost to find a path of negative reduced cost or prove that none exists. And then we'll add new plans and new routes into the master problem. We will iterate between these two components until there is no remaining plan or path with a negative reduced cost, in which case we're going to terminate with the optimal solution of the linear relaxation. So column generation ideas, very standard so far. Now, there are two comments I want to make. Number one is that, well, the structure is inducing a decomposition by fire and by crew in each sub-problem. So you have a master problem that will take care of all of the coordination constraints, kind of the linking constraint between crews and fires. And then each sub-problem will basically find the most efficient route for the crews and the most efficient path for the fires. And then in the sub-problem, so the sub-problem will all be formulated on shortest path on these time-extended networks, so very efficient to solve. But then in the sub-problem, we are going to have this dual constraint, this dual variable, excuse me, that is called rho, that is the dual variable associated with the green linking constraint that will basically link the crew and the fire shortest path together. What does that mean? It means that for every crew, whenever you visit a fire, you get a reward that is given by this dual variable. And for every fire, whenever you use a crew, you pay a cost that is given by this dual variable. David, do you have a question? I see that.
Yeah, yeah. Just a quick question. I understand there's a lot of stochasticity here, right?
Yeah.
Especially in terms of the fire, the path it is taking, and also, did you all also do some in terms of some kind of robust
So
application or
what we do is we implement the model in a rolling horizon.
yeah, but for every horizon itself, every time itself, the fire boundaries and all are very stochastic, right? So we do not
Very
need
stochastic. As
so
I mentioned before, this is one of the limitations. We don't know how we cannot have a stochastic DP into this modeling framework. We need to rethink the optimization if we do that.
fine.
Which can come with benefits in terms of uncertainty management, but at the same time comes with a cost that you can no longer do the crew allocation layer basically. Now this is a great point. We have a deterministic optimization model, and actually this is not the overall framework here is not very easy to incorporate stochasticity into. That's a good point. Let me take a look at the Q&A real quick. Where are we? Prunchal, machine learning model based on any concepts of AI. Okay. So the machine learning model will be used to learn the inputs to the optimization model. And then in the optimization model, we're going to use exact methodologies. So no genetic algorithms or whatever. Like when I talk about column generation, branch and price and cut and everything, this is an exact methodology to solve the IP, the integer program. It's not a meta-heuristic like a genetic algorithm. Okay, so column generation works. It is much faster than the direct implementation of the model by basically an order of magnitude. However, it remains a little bit limited in two ways. The first one is that it only has limited scalability. But then the second one and the most important one, is that it still leaves an optimality gap. And so basically what we need to do is to find ways to restore integer optimality in the column generation framework. And that's why we're going to move from column generation to branch and price and cut. Sorry, there is another question. How's the first function in objective taking care of minimizing crew fatigue by allocating the crew to the shortest path? Yeah, so, okay. So the question here is how to think about travel costs and fatigue here. Well, yes, exactly. Not necessarily allocating to the shortest path, but at least in the cost associated with every path, you have a cost per arc that will tell you basically how much travel you have, how much work you're doing, and then how much time you have since your last rest. And these will be the proxies of crew fatigue and crew cost. And in addition, there is a hidden constraint. It's that you have to come back to base within the time of your next rest, which is very important again in practice. And you have that constraint basically in the admissible set of plans in this formulation. Okay, so two-sided set partitioning formulation leading to a two-sided column generation algorithm, faster, but we have an optimality gap. So we are going to move from column generation to branch and price and cut. So I'm going to go a little bit quickly over that because you have all the details in the paper. I'm more than happy to share details offline as needed. I'm just going to take a little bit of a step back and talk about the general ideas in the interest of time here. Sorry, I'm monitoring the Q&A at the same time. It's a little bit challenging, but he meant to ask a good question between the crew routing and fire plan subproblem. Which one had the more runtime? And I think it was relatively similar. Yes, you can see here, fire subproblem, crew subproblem, kind of similar. So the short answer is crew, but only by a factor of 2. I mean, they are both very, very, very fast because they're just shortest path on a time-space network. Okay. So we want to generate cuts. So for those of you who forgot integer programming terminology, a cut will be a valid inequality that will eliminate a fractional solution, but then keep all of the valid integer solutions into the feasible region. So there's only one idea that I want to exploit here. The main idea is that the linking constraint between crews and fires that says that at any time you have to have a demand for each fire that is less than the supply from each crew, from all the crews, that is basically inducing a knapsack structure. Why? Because you can rearrange that constraint and says that the total demand for all of the fires, so the total number of crews that need to be allocated to all the fires, that's the first term here, plus the number of crews that are idle, that do not suppress any fire, that's the second term here, is less than the total number of available crews. That sounds obvious what I'm saying. Good. But then now here we have a knapsack constraint between our variables. And from the knapsack constraint, we can actually generate what is known as a robust cut. What is a robust cut? That is a cut that will preserve the shortest path structure of the crew subproblem and the fire subproblem. That means that we can encode the cut then in the column generation algorithm by just adding a new dual cost, but that is going to be still inducing the same decomposability for each crew and for each fire, and therefore preserve the very efficient subproblems that we have. Now, the main question in this field is how to generate these cuts. And there is an old answer that was provided by Wolsey in the 1980s, that is the generalized upper bound cuts. So the main idea is the following. Imagine that you have two fires. Fire number one is assigned to 2 crews. Fire number 2, in the fractional solution, remember column generation only solves the fractional, the linear relaxation, so it can have fractional solution. It has basically a value of YQ that would be equal to 0.6 for a plant that has 4 crews, 0.2 for a plant that has 8 crews, and 0.2 for a plant that has 10 crews. Well, then from that fractional solution, you can say, well, actually, you cannot have a crew, an allocation that gives 2 crews to fire 1 and 10 crews to fire 2. Because if you have 10 crews overall as your budget, because then you would clearly have 12 crews that are allocated to these fires that will be in violation with your budget. And so you can add this constraint. That constraint is still correct from an integer optimization standpoint, but it eliminates this fractional solution right here. So in this paper, we strengthen it a little bit because we're doing this in the column generation context. The details are not that important, but then the main idea is that then we are augmenting, we are designing a broader family of cuts that we call augmented generalized upper bound cuts that are essentially looking for more complex combination of fires like this with fractional terms in there. So in this example, for example, I'm saying, well, you cannot have a solution that has let's say 9 crews allocated to fire 3, which is considered here in the fractional solution, and at the same time at least 2 crews or 7 crews allocated to any other fire. And so by doing that, by looking for more complex combinations, you can have a stronger family of cuts than just relying on the generalized upper bound cuts. So again, I'm more than happy to talk offline. I'm going to move on in the interest of time, but these are, the first one here is the generalized upper bound cuts from Wolsey, and the one at the bottom are basically our new cuts. The main difference is that we have this delta parameter here that are fractional terms that are therefore allowing a more fine-grained linear combination as compared to the generalized upper bound cuts that you're seeing on the top. And the main theorem from this part of the paper is that if you add all of the augmented GUB cover cuts, you get a tighter linear relaxation than if you add all of the generalized upper bound cover cuts.
Two questions, Alex. I think this is the right time maybe to take them. One is approach scalable on large wildlife scenarios, multiple crews, any kind of computational challenge that would come through or anything? Or these
Yeah.
are
If I can just table that question for 2 minutes, I'm going to talk about the last component, and then I will really answer the question with numbers. Okay, so now we have column generation, cutting planes. The last thing we need is branching, right? Branching down with column generation leads to branch and price. So we're going to have a branch and price and cut algorithm. So so this table, this figure just tells us the augmented GOB cuts can actually improve upon the GOB cuts. Good. So at this point, we can solve the linear relaxation well, but we still need to do branching. So for all of those, all of you that have worked on vehicle routing, whenever you have a column generation and branch and price algorithm, you do not branch on the path-based variables. You branch on the natural variables, right? You don't say either you take this plan or that plan, because otherwise you're going to have very large and imbalanced trees, which is not good. So what you're going to say is like you're going to go back to your original arcs and you're going to say either you go through that arc or you do not. So in this case, either the fire has a demand of D or does not. And either that crew suppresses that fire at that time or does not. Now, so far, very standard. However, there is an important distinction with traditional vehicle routing. So what is that? It comes from this instance where you have a fractional solution at the end of your column generation that essentially assigns, let's say, 2 crews to one fire with a weight of 0.5 and 4 crews with a weight of 0.5. So in this case, the average number of crews is actually 3. So in vehicle routing 101, we just say, well, the optimal solution is 3. And this is fine because you have linear costs. But in our case, we have a very non-linear system. Like, remember that each fire cost is governed by a dynamical system that is non-linear. So what is difficult here, I mean, the difficulty is that the cost of the average plan is not the average cost of the plans. So the linear relaxation that takes 0.5 of this and 0.5 of that can have a cost that is very different to what would actually be achieved with three crews. And so basically the traditional branching rules in branch and price, like most fractional branching and this type of things, may not lead to an optimal solution. In order to illustrate this point, let me look at, for example, the one in the middle here. Imagine that you have a fire where in the fractional solution, you allocate 5 or 6 crews with weight 0.5, 0.5. Then most fractional branching will tell you, oh, wow, you have no idea, it's 5.5. 5.5 is quote unquote very fractional, branch on that. But from a practical standpoint, I'm like, you kind of know what to do, 5 or 6. I mean, there is consensus here from the fractional solution. 5 or 6 doesn't matter that much, potentially. This fire, however, I don't know what to do. My solution tells me perhaps 0, perhaps everyone. I mean, this is as extreme as it gets. And then most fractional branching in that case would actually deprioritize that fire because the average is 5 and is integer. And so essentially, we have a very new branching rule in this paper that will actually look at what we call maximum variance branching, where we're gonna take a probabilistic interpretation of these fractional solution numbers, and then we're going to prioritize the fires and the fire time pairs, basically, where there is the most disagreement within the fractional solution. So in this case, we're going to branch on the third fire rather than the first or the second. And so this is the idea. Essentially, we are going to branch on the variables that have the maximum variance that are also weighted with the dual prices to identify kind of high leverage fires. And so basically our main theorem is that with this branching rule, the overall algorithm converges in a finite number of iterations to an optimal solution, which is what we're trying to prove in general in branching price papers, whereas fractional branching may not. So this is the overall algorithm. You have two-sided column generation. You add your cuts, the augmented GUB cuts. Then potentially you can call a heuristic. We have a heuristic that is developed in this paper for upper bounding. So you get a feasible solution. So now you have a lower bound, you have an upper bound. And then whenever they do not match, you start branching. And then you start again in each node. And then you keep going along your branching tree. I'm going to skip the heuristic. And now I'm going to this results table that is now answering the earlier question. Let me talk about the good news first. The good news is that the augmented GUB cuts actually work. In small instances, they reduce the computational cost by a factor of 2. And in the larger problems, they actually reduce the optimality gap. Number 2 is that dual-aware branching works really well. It reduces the computational times by 1 order of magnitude and enables to close optimality gaps. And the primal heuristic also works and is very useful because without the heuristic, we actually do not get even a feasible solution within 20 minutes of computation. Whereas with the primal heuristic, we can get a solution within 2% of optimality. And then when I take the entire algorithm and I try to scale it and scale it and scale it, we actually get optimal solution with instances of like 20 to 30 crews or up to 5 to 10 fires. We can push it to like 70 crews and 20 fires, and we get an optimality gap of 5%, which is actually a very, very, very difficult optimization problem. And so getting to like 5% of optimality was something that we were really hoping for. And perhaps the last thing I want to say is that the benchmarks of all of the other benchmark, which is direct optimization with Gurobi or like more simpler column generation implementation, would lead to very poor performance in comparison. And so we are able to derive significant performance improvements as compared to all of these benchmarks. So I hope that starts answering your question. So basically, the main challenges from a computational standpoint would be obviously the size of the problem, number of fires, and number of crews. And then also very importantly, it's the underlying fire representation. So if I go back here, the granularity of this time state network here is going to impact the scalability of our problem very significantly. So if, for example, you want to have a very fine-grained, high-dimensional representation of your fire, so a very large state space, then obviously you're going to have a granular representation, which is good, but then at the same time, you're going to have a much larger model, which is bad. And so that's the type of thing that you want to trade off when you're looking at these things. Let me stop for a second. How does one tackle with the problem of robustness? That is an excellent question, Rohit. So again, in our paper, what we do is that we implement the model dynamically. We do not incorporate stochasticity within the dynamics themselves, but we are implementing it dynamically, and we are showing that we actually can get good solution over time. I think that the idea of like making this model more stochastic or more robust is a very fruitful avenue for future research. The challenge is that it's difficult to do so in a time-expanded representation like we're trying to do here. The same thing is true for the question from Yasvinder, which is about forecasting ignition hotspot. So that we don't do. What the machine learning model, which I'm going to turn into now, what it will do is that it will it will predict the evolution of the fires that we know. We don't really consider new fire risk in this machine learning model. Again, lots of future work, lots of future work. All right. Since we have a little bit of time, I'm going to spend 10 minutes on this machine learning problem. I think it's very interesting by itself.
Yeah.
So is that okay? Yeah, okay, good.
Yeah.
So we have a bunch of fires. We have a lot of crews. Each of them has a lot of firefighters. I mean, basically, we have this overall case study problem. The question is, for each of the fires that we're looking at, predicting their future evolutions. And in that sense, we can think about it as a machine learning problem. So on each day, we want to predict the evolution of the fire on the following day. So if we think about this from a machine learning standpoint, what are going to be your features? Current fire size, maybe recent fire growth. We call that momentum of the fire. Meteorological information, again, precipitation, humidity, winds. Local vegetation, very important. Time of the year. These type of things, right? I'm checking the Q&A again. Okay. Okay, so these are the variables that will matter. However, from an optimization standpoint, I don't only want to predict what's going to happen tomorrow. I want to understand what would happen if I send zero crews, 1 crew, 2 crews, 3 crews, 10 crews, right? So we want to actually predict the future evolution of the fire as a function of your suppression allocations. So not only as a function of your satellite data, but also as a function of the crew allocations, meaning your decisions, right? So you want the future state as a function of the current state, your covariates, but also your decisions. You want to learn a dynamical system. You don't want to just learn an exogenous behavior. And that is very difficult to do from a machine learning standpoint. Let's think about it for a second. Why is that? Well, fire managers are very skilled. If you have 2 fires, so think about it for a second. If you have 2 fires, a big one and a small one, you want to predict that the big one will grow faster than the small one. Okay, good. But then you want to predict that, you want to look at how much they will grow if you send 0 crew, 1 crew, 2 crews, 3 crews, 4 crews. The problem is that in historical data, you had more crews allocated to the big fire than the small fire. Why? Because fire managers are smart. They know that this one is dangerous. So they did allocate 3 or 4 crews to this one and 1 crew to this one. You with me? Shout if you're not. Unmute yourself and talk. Does that make sense? So now, why does it matter? It matters because if now you put crew as just a feature into your machine learning model, then you will learn what? That more crews lead to more fires, to bigger fires, because more crews were allocated to high-risk fires. Right? So if you just put that into like a simple regression, you will actually find that the effect of a crew is to make the fire bigger, which is obviously nonsensical. Okay, so now we need to merge a problem in machine learning, which is predicting all of this with high-dimensional data, and econometrics or causality in order to estimate a treatment effect. And so this is what we're doing here. We're going to use a recent method that is called double machine learning to mitigate the confounding between fire characteristics and crew assignments. So this is how the method works. So this is also the reference for those of you who are interested. It's a beautiful paper. I recommend it. And so basically, what we have is this, is that you have covariates X, you have an outcome variable Y, and you have a treatment variable T. So, but the fundamental equation is that the outcome T depends on the treatment. So treatment in that case would be crew allocations. Covariates is all of your meteorological information. And so you're saying that the outcome depends on your treatment and your covariates. The problem is that your treatment depends on your covariates as well. And you want to disentangle these two effects. So the way this method works is that you are basically going to first estimate Y and T as a function of X without looking at the interaction. So you're gonna estimate your fire growth as a function of your meteorological information. And then separately, you're going to estimate your treatment, so the number of crews that were assigned historically, as a function of meteorological information. And then you will compute the two residuals. So the residuals in English mean the unexpected growth of your fire given meteorological information, and the unexpected crew allocation given meteorological information. So by looking at the residuals, we're basically orthogonalizing these variables a little bit. And now this is enabling us to do a stage 2 prediction where we're predicting the residual outcome as a function of the residual treatment and the meteorological data. Okay, so that's what we've done. Let me, if there is no question, I'm going to continue a little bit to some results. We basically found that this approach was giving us a good predictive model with a low RMSE, MAE, high R square, low shortfall. What we found is that we had the best success with light GBM models, both in the first stage and the second stage. What we also found is that actually traditional machine learning models, single stage machine learning model, were not doing too poorly when it comes to like just estimating the error on the points that we actually have. But then when we actually looked at the full treatment effect curve, then we had really the nonsensical behavior that I was mentioning before. If you look at this regime here, you can find indeed that sometimes more crews would lead to bigger fires if you do like traditional machine learning in red. You see? So this is like the fire growth on the y-axis and the number of crews deployed on the x-axis. In this case, you see regimes where you have more crews leading to bigger fires, which is really the type of thing that doesn't make sense in practice. In contrast, the blue curve, which is the one that we learned here, has a smooth, non-monotonic, and non-linear relationship that we're trying to learn. It all comes with a lot of noise. This is a very difficult empirical problem, but nonetheless, it is indicative of the type of curves that we want to retrieve, and so we were also, it also gives us like some snapshot into feature importance for interpretability purposes. So we find that fire growth is a function of your treatment, meaning how many crews you allocated, the history of your fire, meaning the current size and the current growth, environmental factors, and time of year. And with this, we were actually able to replicate the fire state. So it took me an hour, but I finally answered your question. How did we come up with this network? Well, here we go. We have it here. Sorry. So this is basically the fire state model that we have. The y-axis represents the current burn area. The x-axis represents time, and then the color of the transitions represents the number of crews that you're allocating, or the number of firefighters in this case. And so So here you can say that you have a fire that is very small, but then if you allocate no crew, it will grow, it will blow up. However, if you at some point deploy more crews, it will actually reduce. All right, so this is a snapshot of our final results that are basically combining this data-driven machine learning model into the optimization. We're seeing like the spatial temporal allocation. So in this case, we have one fire that we are trying to suppress very early on because it was blowing up. And so here, after that, it is suppressed. Then Silver Creek, we let it grow for 3 days, and then we actually eliminate it on the 3rd day. And then you have other fires where, for example, you would, going back to one earlier question about preemption, Natchez, we start on day 1 and then we actually go elsewhere because Silver Creek becomes bigger, and then we finish on day 5. So we start on day 1 to prevent it from blowing up, and then we suppress it on day 5. And so the idea is that really what optimization is doing is to fine-tune crew allocation decisions based on the impact of the wildfire, but also, and so all of these propagation dynamics in time and space, and also the crew routing considerations and what a crew can feasibly do. All right, that's my talk. Optimization methodology for wildfire suppression. I think it's an interesting optimization structure because it combines a difficult routing problem with some endogenous demand, so some dynamical system. So if you view it that way, you have a very, very non-linear routing problem, which is difficult to deal with, and the set partitioning formulation circumvents the non-linearities. It comes at the cost of an exponential number of variables. So to do so, we have developed like this branch and pricing cut methodology based on two-sided column generation. We show that it can actually solve meaningful problems, and at the same time, it led to an interesting data-driven problem to fit this representation from historical data with a significant endogeneity or confounding problems because of to retrieve causal treatment effects. And we have now implemented this double machine learning methodology to do so. Thanks again very much for the questions, for the invitation. I'm going to look at the last questions. Can I share my slides? Yes, that's easy. And then another one on the Q&A, Himanshu, that says, can we say that endogeneity is due to simultaneity bias and to unknown functional form, which is why we're using two-stage, that we're using DML rather than two-stage D-square. Data imbalance makes standard parametric techniques less useful. Yeah, these are all great questions. The endogeneity bias is indeed due to the simultaneity bias, 100%, because you are jointly allocating the crews and observing your fires. The unknown functional form, I view it as a kind of a separate. It's like you want to have a method that is allowing nonlinear relationships here, which is why we went to DML as compared to two-stage D-square, because we wanted to capture the nonlinearity in this response. That's very true. And also the high dimensional data, which machine learning is very good at. Data imbalance, I haven't thought about it that much. I don't think that our data it's hard for me to think about data imbalance in this case because it's a regression problem. And so yes, you can view the distribution as an embodiment of data imbalance, but I haven't really thought about data rebalancing techniques in this context, like, upsampling, downsampling, and this type of things. Good question. I need to think about this. I don't know, short answer. But great question. If we track the travel sequence of the crew with IoT, would it give more dynamic inputs to the algorithms? I think that we have the sequence of the crew, and so basically it will give us more granularity, maybe in the way we can calibrate some inputs like for example, travel times, travel costs, and this type of things. I think that right now, I mean, the fire managers do have IoT information regarding where the crews are at any point in time. I think that the more significant challenge is to get real-time satellite data in terms of like exactly what fire you have and how risky they are. So kind of training these prediction model in real time. I think that the challenge is much more on the fire side than the crew side in terms of real-time visibility and IoT opportunities. Which tool, Umatanta, I'm not sure I understand the question. Which tool I used? I don't know what that means. Sorry.
Software, so probably any softwares or something that is used in the whole modeling, any machine.
Oh, well, we have trained all of our machine learning models on like standard Python pipelines, and all of the optimization models on Julia Jump. And mainly the one thing I want to leave you with is, again, this slide. Transportation and logistics and optimization are not all about, like the traditional applications. The traditional applications are fantastic. Devjit does a great job at them. I have enjoyed them a lot, and I still do. But there are also other emerging problems where the similar challenges are arising, and also what is exciting is that these new problems are not exactly like what we are used to, and that is actually requiring more methodologies and more innovations on the new data, new structures, and new problems, new technical challenges, requiring new innovations and new methodologies. And I think that this back and forth from problem to methods is really what makes it so much fun to be in this space, honestly. And I encourage you to look at new problems overall, because that's what is so wonderful in research. I see one more question over there. If I could please show where do the estimates from the prediction model fit into the optimization model? Right, okay. So let me go back into that one last time. Basically, the predictions gives us this type of things. Growth at time t+1 as a function of your crew deployments. And from that, you can actually reconstruct these fire state time state networks, which is basically every transition here is learned from the machine learning model. And then once you have this, that is essentially giving you this representation on the right that will then feed into the optimization model. And I think I answered all the questions. If I did not, let me know.
I think it is fascinating. The problem itself is super interesting, Alex. I think we know about how crucial this problem is, but how do you leverage machine learning in developing the crew assignment and all was really fascinating. I think it's very interesting. So thank you so much this evening to make this talk super exciting. We are really, really thrilled. And hope to host you in person sometime, Alexander, in India. Yeah, you should visit us.
Yeah, I would love that. That would be wonderful. Thank you so much again for the invitation, and it was great to engage with you all, and thanks for the questions and the attendance. If you're ever at some conference where I am, feel free to come and say hi in person to everyone. And Devjit, I don't know if I'll see you at Informs. I hope so. And if you ever work on related problems, feel free to send papers anytime. I love to read them. I love to share them with my students, so they can learn about what you all are doing. I love to include them in the syllabus of my class. So keep up the good work, and stay in touch.
Thank you so much, Alexander. Thank you all for joining this evening for our research webinar. Stay tuned for our upcoming workshops and other things. So thank you all. Thank you, Alex, for making this event successful. Thank you.
Thank you.